So I mean, there was some work which I assigned last time, but yeah, let's continue to look at completeness, okay? Because I think this thing is essential. So let's continue to look at completeness in metric spaces. Right. So so far, what have we proved in here, right? So we have proved the following thing, yeah, and it's like given a metric space X comma D, yeah, there exists a metric space X prime comma D prime. So when you say a metric space, it's this pair is called a metric space, right? The total data of a metric space is this set X with the metric D, okay, right? Such that, right, such that given, yeah, I would like to say in a slightly different way, such that given any complete metric space Y comma D1 and a continuous function. I mean, it all sounds very abstract, but I mean, if you go back and specialize this to things that you know, then you will find it quite nice. Like you can take a Q and R, you can take bounded, you can take like maybe collection of polynomials and see, you know, if you, that's like polynomials, and then look at them as functions on, let's say, 0 comma 1, and consider may try to make a metric space out of it, and then think like, is this complete? What will its completion be? And that's interesting questions, right? So you can think, right, a continuous function, this, and a continuous I'll say map, because gradually the function will become a special kind of map. So a continuous map from X to Y, yeah. Then there exists a unique map. There exists a unique F tilde. Yeah. Okay, so I should say a little bit more. Maybe with maybe this I, and I is a function from X to X prime. Yeah. Don't worry about like you know, because see, you don't have to. This is the kind of thing, you know, even if you don't know all the details here, that's not like, maybe your thinking is very complicated, but you see, you know, we'll have to make things work. So uh, this thing is such that, and of course this is continuous. It's continuous. Then there exists F tilde from X prime to Y, such that the following thing happens. And of course, F tilde is also continuous. So every map is continuous. So let's see what happens, such that, as you can understand, you have a map from X to Y. Yeah, this F. You have this I, right? Then there exists a map from X prime to Y. So this will look similar to what you have done. I'm sorry, the maybe the definition of of completion of a metric space I told you. Okay, but today I'm trying to state it like this and see if this means if this gives you that definition, this more abstract and maybe more algebra looking definition. So again, let's try to understand. Okay, so yeah, let's think of x as q. Okay, and let's think of this as r. Okay, and let's see that if we have some metric space y, then you have the natural inclusion. This is the inclusion function. And now I'm saying that if you have a function to any other metric space, any continuous function to any metric space, can you give a function from here? First, let's ask this question. That what I said there, this is not a question at all. It's just a statement, kind of just saying that x prime is there with these properties, so many properties together. If it sounds like that, but it's actually not. But let's think about this. Can we quickly give a map from R to Y? So Y is a complete metric space. We need to use that fact. Right? So please think about it. Please think about it. This is a more concrete question. Right? Given a function from Q to R, then can you Q to Y, can you find a map like this? What this is just saying, as you can understand, is can you extend the map from Q to R, right? You have a function f which is defined on rational numbers, right? It's defined on rational numbers. Can you define it on real numbers? Can you? That's just a simple way. This is just a complicated way to say that, because if you take a rational number, right, you send it here by p by q, you send it here, and this is just going to p by q, right? And the function that you will construct, it will be the same. It will also take it to p f of p by q, right? So on rationals, it will do this new function, whatever function you create, let's say g or f tilde, it will do the same thing as f was doing, but now on q. But now on elements on R which are not in q, what should it do so that you still get a continuous function? Right? So that is the thing. Okay, I hope the question is clear. You have a function on rationals, you want to extend it on all the reals. It's as basic as that. I'm just asking if it's possible or not. Okay. Right. Okay. So, well, let's see. Should not be difficult. Yeah, any ideas? Should not be difficult. Take your favorite, irrational number, let's say root 2. You want to make sense of f on root 2. Or same thing as saying you want to define f tilde of root 2. How would you define it? How should you define f of root 2 or f tilde of root 2? Right? Well, you see, root 2, you can write root 2 as a limit of rationals. Right? That is the point, right? you want to extend to R. So if you take root 2, you think of it as limit of some rationals, correct? So then it's this, right? But now you know that your function is continuous. The function is continuous, right? So this should happen. This you know is continuity, right? I mean, notice that this is not defined yet. This is maybe just put tilde. F at root 2 is not yet defined. We are defining it, trying to define it. If there is a definition, what should it be? Correct? It should be just this. Yeah, if this number exists, then it should be this number. If it doesn't exist, then it's a different. If this number exists, then it should be this thing, right? But then you see, f of Pn by f of Pn by Qn, this is the thing. And well, by continuity, you know that this sequence should converge, right?
Yes.
Yes, that's correct, right? So if Pn maybe as simply if An converges to A, right? Then you know that f of An should also converge, right, to f of A. Yeah. So, but then there is a small problem, and the problem is that okay, An is converging to A. This part is perfectly rigorous because Pn by Qn converges to root 2. Okay. Now, when you take f of An and you take its limit, you consider this quantity. Yeah, I mean, so how do you say that it converges? Because, well, the problem is that if f was already defined at A, then you could say that it converges, right? But right now, I mean, you don't know if f is defined at A, so you cannot really say that. So point is that f is a function from Q, right? F is a function from Q. So how would you say this? F is a function from Q. So yeah, like this doesn't make much sense, right? This is just our definition. Like we should define it like this. Yeah, then just define it. No, correct? No problem, right? Yeah, just define it like this. No, so that is just F. Yeah. But let me see, is there something which we are doing wrong? Yeah, it feels like we are doing something wrong. Yeah, but then it is not. Wait. There is some problem. See, the question to ask is, does exist? Yeah. If f tilde was already continuous and it already existed, then this limit would exist, no doubt, by continuity. But right now, can you say that this limit exists? That is the question. It's not completely clear, right? Do people see the point? If you don't know that the f tilde exists, then how do you know that this limit exists? Because f tilde f at root 2 has no meaning, right? You cannot say that its limit at root 2 exists. You cannot even say that. So can you say that this limit exists? Well, if you cannot find anything to say it, it's probably that it doesn't exist. Like it doesn't have to exist in general. We need some conditions, right? So let's take an example, I think, where it does not exist. Okay. Yeah, so if you have any function from rationals, but anyways, maybe rationals is a little, if we just think about it very simply, let's see, the situation is all the same like this. If you have this function from, if you have this 0, 0, 1 open, right? And you define this function fx equals to 1 by x, right? Okay. Then as you can understand what I'm going to do, right? If you take an equal to 1 by n, right? Then you take f of an. An is in the domain, right? An is in the domain, right? Or whatever, right? But yeah, is this, right? But does this limit exist? Does it exist? No, it's infinite. Correct? Doesn't have to exist. That is a problem. So hello, am I audible?
Yeah.
Right. So is my
Yes.
point clear, right? Yeah. That you just because you have a sequence which converges, right, to something, it can be something outside, so this is now your x, right? This is your x, and you have a sequence in it that converges outside, right? And but then you are not able to extend it because, so basically you cannot extend f to closed 0, 1. So in the same way, and you can kind of see that, I mean, you would like to say that this is the completion of this, right? This is a complete metric space that you should know, you should prove it. And this, okay. So then, yeah, then the thing is that this statement is sort of, that this statement is not very nice, right? Then how should you modify this statement? Okay. Or let's keep focusing on the red diagram and ask the question, what condition should I put on f so that I can extend it, right? What condition to put on f, yeah, so that, I mean, you understand, so that f tilde exists, so that I can extend it to a continuous function from R. That you should think. It's going to be uniform, I mean, but yeah, you think about it. What do you think? So you should think about this. Okay. So I'll frame the question clearly on a new page, and then you should think about it for next time. And now I'm framing it very concretely. Okay. But you should always try to connect it with those diagrams and see what it means. Okay. So concretely speaking, f is a function from Q to a complete metric space. Let me make it R, even more concrete. Okay. F is a function from Q to R, continuous. I'm not writing continuous. Okay. Yeah. What condition, or maybe when can X be extended? When can F be extended to a continuous function from R? Okay. So it's clear. Question is clear. Think about it. What condition should you, what minimal condition should you put on F so that it happens? All right. And then, yeah, you can even think about this case and probably you will get some. And this is a very standard question. You look at any analysis problem solving book like Axor or something, or you look at any theoretical book like any metric space book, this is there. Okay. But first I would encourage you to think like what will ensure that this limit of Pn by Qn exists. Okay. What is it in our, what are we given that will allow, yeah, what is the definition of completeness? Cauchy sequences converge, so on and so on. Try to think. Okay. But now let's, so you saw some problems, like some restrictions on uniform continuity has some restrictions, right? But now let us go back to this abstract setup. Okay. And yeah, let's get back to this abstract setup and see. Or maybe we can talk about this abstract setup also next time, because I mean right now you don't know what extra you should put here, and unless you, it's good if you first figure it out in the concrete case, then I will put that condition there, and then we will see if from this definition we can that from this strange looking condition for now, can we just from here, can we say that X prime is the completion? That means X prime is a complete metric space, which is not given, but will it follow from the X prime satisfying this, exotic looking property? Will it also follow that X is dense in X prime? So many other things. So yeah, I mean, you should think about it, about that concrete set and setup, and then. So that was the first part, which I wanted to talk about completeness, but this is more of a abstract side. You can try to apply this thing. You can try to apply this completeness of R. So maybe after we meet, we can just after the break. So today I will not go for very long, but what I will want to do is we want to apply. Yeah? We want to apply completeness of R. Okay? So, well, you know that R is complete, right? And that just means that every Cauchy sequence converges, or there are other properties. So we would like to apply the completeness on R to, to try to show that some other spaces are complete. And my goal would be to do some important theorem. Yeah, maybe I will prove this result, which is very important. You look at the continuous functions on 0, 1. look at the collection of all continuous. This is also something we should study. This space of continuous functions on 0, 1, and we will show that this is a complete. But of course, when I say complete, then you should ask what is a metric. And here we will consider the sup metric. The distance between two functions will be the supremum. So yeah, you will want to show that this is a complete metric space. It's a very, very important result. So when I say this, I obviously mean functions whose range is R. Okay, functions whose range is R is a complete metric space. Okay. Yeah, this is certainly an important result. And another result which we want to prove is also has a lot of significance, but I will not state it right now. We will look at this first. Yeah, so we'll do this after we meet, and probably that will be all. Okay, but yeah, you should do all these exercises and things which we are looking at, and then we will try to prove this when we meet. Okay? Yeah, and then I will suggest you some other similar exercises. All right. Okay. So let's meet in 10 minutes.